Okay, so there's a couple of questions about the exam for this Friday. So the exam on this Friday will literally just cover, or excuse me, the in-class portion of the exam on this Friday will just cover parallel RLC circuits and series RLC circuits. You will be expected to analyze a single parallel RLC circuit and a single series RLC circuit. One of them will have a dependent source, the other one will not. Okay, so it's literally just two problems pulled almost exactly from your homeworks 8 and 9 or 9 and 10 or whatever the hell we're up to. Arguably probably a little bit easier so that you can knock two of them out in the hour and 15 minutes that you have allotted. So if you have been keeping up with your homework, the take-home, the in-class portion of the exam should be a joke. All right. The in-class portion, damn it, I keep getting it backwards. The take-home portion of your exam will be based on what we're covering today and Wednesday, which is general RLC circuits or circuits that do not fit neatly into the buckets of series RLC or parallel RLC. So we are going to extremely slightly review a couple of things here really quickly before we get into them. So total response of general RLC circuits. So to review very briefly about what we've done to this point, let's look at a parallel RLC circuit over here on hopefully just the left. So we might have something like this. Where this will be our voltage drop, V of t, and this is the current flowing through our capacitor, IC. This is the current flowing through our inductor, IL. This is the current flowing through our resistor, IR. And I'm just going to breeze through these steps because you've all seen them already. So if we were to apply Kirchhoff's current law, we would find that IR plus IL plus IC all equal together to make 0. Using the appropriate relationships, this would look like V over R plus 1 over L times the integral from T naught to T of V prime, excuse me, V of T prime. dt plus IL at T naught plus C, excuse me, dV by dt is equal to 0. Taking the derivative of both sides and moving some stuff around, we wind up getting the second derivative of the voltage with respect to time plus 1 over RC times the first derivative of the voltage with respect to time plus 1 over LC times the voltage with respect to time is equal to 0. And we found that this circuit had a characteristic equation of S squared plus 1 over RC times S plus 1 over LC is equal to 0. I'm going to call this coefficient right here B, and this coefficient right here C. And then over here on the left, it takes up as little space as possible, we found that alpha was defined to be 1 over twice RC, which is literally just that coefficient I've called B divided by 2. And omega naught was the square root of 1 over LC, which is just the square root of that coefficient I've called C. Right? Those are the results of our derivation, and then we got into our response equations and this, that, and the other. Now, let's look very briefly at a series RLC circuit. So, here's our simple series RLC circuit. This is R, this is L, this is C. This is our common current I flowing around the circuit. This is VL, VC, and VR. Applying Kirchhoff's voltage law, we could see that VR plus VL plus VC was equal to 0. We can express all three of these in terms of the current. So that is R times I of t plus L di by dt plus 1 over c times the integral from t naught to t of I of t prime dt prime plus I at t naught is equal to 0, taking the derivative of both sides and doing a little bit of rearranging. We wind up getting the second derivative of I with respect to time plus R over L times the first derivative of time, or the first derivative of the current with respect to time, plus 1 over LC times the current is equal to 0, which had a characteristic equation of S squared plus R over L times S plus 1 over LC is equal to 0. Once again, I'm going to call the coefficient of the S term B and the constant term C. And we found that alpha was R over 2L, which is literally just coefficient I've defined as B divided by 2. And omega naught was the square root of 1 over LC, which was nothing more than the coefficient that I'm calling C, and then we take the square root of it. So it seems, based on our prior experience, that for any generic RLC circuit, if I can put it in a second order differential equation form, where the coefficient of my second order term is 1, If I divide the coefficient of the first order term by 2 and take the square root of the constant term, I will be able to figure out what alpha and omega naught are for that particular system. So we're going to use that approach to analyze some circuits that don't easily fall into the parallel RLC and series RLC classification. So let's take a look at this guy right here. This is an example of a circuit that is neither a series RLC circuit or a parallel RLC circuit. Now, if our switch was opening in the opposite direction, meaning that our switch was opening at t is equal to 0 instead of closing at t is equal to 0, this would be a series RLC circuit. But because the switch is closing, what we're going to have is a resistor R1 in parallel with the series combination of R2 and L in parallel with a capacitor, which is by definition no longer a parallel RLC circuit because we can't combine the resistances into a single equivalent resistance, okay? So we can't just use our parallel RLC circuit rules. We have to apply the generic approach. So I am going to define the voltage drop across the inductor having this polarity, the current flowing through the inductor having this direction, and I'm going to define the voltage drop across the capacitor having this polarity, and the current flowing through the capacitor having this direction. And our goal is to get a second order differential equation of the following form. So we're going to need something that looks like either d squared v with respect to time squared plus some coefficient b times the first derivative. Sorry, this should be vc. I'm just going to call this an arbitrary constant k, so it doesn't necessarily have to be 0. It could be some non-zero number, but it's just going to be a number. So we have to get it something in this form or the exact same form, except that it will be in terms of inductor current as opposed to capacitor voltage. How we do this is irrelevant, okay? So we can employ nodal analysis, mesh analysis, and things like that. I would argue that it usually comes about to be more of a pain in the ass than if we had just done KVL, KCL, and Ohm's law, but it is technically possible to do this using nodal and mesh if you guys are just hell-bent on doing that. I'm not going to do that because it comes out to be a huge pain in the ass. So instead, I'm going to use a combination of KCL, KVL, and Ohm's law for this particular circuit. And then if we have enough time, I might run through it using mesh or something like that just to show you that it winds up being a pain. All right. So one caveat that I have here is that our differential equation needs to be written using the circuit while it's in its transient state. right? Because the transient state is what's governing that second order differential equation and all that kind of stuff. Or actually the other way around. The second order differential equation is what's governing how the voltages and currents behave during the transient condition. So during the transient condition, the switch is closed. So I might write a Kirchhoff's current law equation. So something like this. So let's say I have this current flowing in, this current flowing out, and this current flowing out. So that might be, so let's see, the current flowing in, I could write as Vs minus Vc divided by my resistor R1, where effectively I'm just treating the bottommost node as if it were ground. Another way to think about this would be doing KVL around the outside loop and solving for the current that's flowing through the resistor R1, same thing. Plus, excuse me, is equal to IL plus IC. Okay. So that's me applying Kirchhoff's voltage law at this node right here. And at present, this equation contains my capacitor voltage, my inductor current, and my capacitor current. Since I know that I want things only in terms of my capacitor voltage or my inductor current, I'm going to choose to represent my capacitor current as a function of capacitor voltage, right? I'm also going to rearrange some things here really quickly, right? So I might say that IL of t would be Vs divided by R1 minus Vc divided by R1. I'm just splitting that fraction thing up into smaller parts. When I move IC to the other side of the equal sign, it's going to have a negative sign. So I would have minus, and then I know that the current flowing through a capacitor is just C times the derivative of the voltage drop across the capacitor. So that would be C dV by dt. And so this to me looks like a pretty darn good equation because I have my inductor current expressed only in terms of constants and my capacitor voltage. So I'm going to call this guy right here equation 1, and I hopefully won't have to mess around with it anymore, but maybe I will. We'll see. Don't know what I did with my notes, so I'm just freestyling up here. The next thing that I might do is write a Kirchhoff's voltage law equation. And I'm going to choose to write my KVL equation around this path. And I'm choosing this path in particular because I know that it's going to relate my inductor related quantities to my capacitor voltage because all of that's going to show up in this KVL equation, right? So I can see that my capacitor voltage Vc is going to be equal to the voltage drop across resistor R2, which is just going to be R2 times IL, as well as the voltage drop across my inductor, VL. Are we all okay with that? And I can substitute in for my capacitor, or excuse me, for my inductor voltage, I could say that that is L times the derivative of IL. So I'm going to call this equation 2. Okay. And so I've got two, just in my opinion, utterly fantastic equations here. And so I can kind of choose my own adventure as to how I want to combine these things. Now, my end goal is to get a second order differential equation. And right now, both of these equations only have first derivative terms at its maximum. So what I'm going to do is I'm just going to take the derivative of one of these guys, and I'm going to choose to take the derivative of equation 1, okay? So taking the derivative of equation 1 is going to give me the derivative of IL with respect to time is equal to, so what's the derivative of Vs over R1 with respect to time? 0, because both of those things are constant, right? So then I'm going to have negative 1 over R1 times the derivative of my capacitor voltage with respect to time. And then I'm going to have negative C times the second derivative of my capacitor voltage with respect to time. Let's call this guy right here equation 3. So what I can do now is I can just substitute in equations 1 and equation 3 into equation 2. And I'll wind up with a few algebra steps in between a second order differential equation. So in my second equation, I have VC is equal to R2 times IL. Well, IL was defined in terms of VC in equation 1. So that's going to look like Vs divided by R1 minus VC divided by R1 minus C times the derivative of VC with respect to time. And then I have plus L times the derivative of IL, which was defined in equation 3. So that'll be negative 1 over R1, the derivative of my capacitor voltage with respect to time, minus C times the second derivative of my capacitor voltage with respect to time. And from here on out, it's literally just algebra to get it into the form we want, okay? So I'm going to move all of the capacitor terms from the right-hand side of the equal sign to the left-hand side of the equal sign so that they're all going to have a positive number or positive coefficient. So let's look at our second derivative term first, right? So this L and this C are going to get multiplied together. And so I should have LC times the second derivative of my capacitor voltage with respect to time. Just for organization's sake, I'm going to put a check mark above this term to let me know that I've already moved it over to the other side of the equal sign and all that kind of good stuff. Now we're going to deal with the stuff that is the first derivative term. So I have an R2 times C. So that's this term right here. And then I'm also going to have an L over R1. That's from this term right here. And I believe those are my only first derivative terms. So now I have my, what I like to call my 0th derivative terms, or my, just the function VC by itself. That'll be plus. So this guy over here is going to contribute a 1. And then I'm also going to have plus R2 divided by R1. So that's taking into account this guy and this guy. And this will be equal to Vs multiplied by R2 over R1. And realistically, I can go one step further, which is just, yes, Toby. Why? So this term right here has a negative sign when it's on the right-hand side of the equal sign. I'm moving it all over to the left-hand side of the equal sign to get rid of all of the negative signs on the capacitor terms.
Everything that yes,
Exactly right. Yep. So as I was saying, realistically, I could bother taking an entirely separate step here and just divide everything by LC to make sure that my coefficient on my second derivative term is 1, but I'm lazy and we can very obviously see that that's how things are going to work. So my coefficient B is going to be R2 times C plus L over R1, all divided by LC, which means alpha for this guy is going to be R2 times C plus L over R1 divided by twice LC, because alpha is just whatever my coefficient is for my first order term divided by 2. And then lowercase c is 1 plus R2 over R1 divided by LC, which means omega naught is just the square root of that. And from here, I can just compare alpha to omega naught and know whether or not I have an overdamped, critically damped, or underdamped circuit, and everything else is the exact same thing that we've been doing. The only difference is that we have to write our own second order differential equation to figure out what alpha and omega naught are. Every step subsequent to this is the same crap we've been doing. Okay. All right, so do you want to make this suck with mesh? All right, I'm done for today. Yeah.
So whenever we're given like real numbers instead of just variables, do you recommend doing it with the variables first and plug everything?
Yeah, so remind me of your name because I'm an asshole. Holden. So Holden asked a very, very good question. He said, if we're given numbers, should we work everything symbolically or should we work it with the numbers? I am a huge proponent of working everything symbolically because I find that I make way more mistakes moving the numbers around and all that kind of stuff, much more so than I do by moving the symbols around. I can't force you to do it that way, but I think you will find you will get way fewer mistakes in the algebra if you work everything symbolically. And given that the algebra in these can get quite complicated, finding an error can be a bit of a pain in the butt. So, yeah. Landon. This homework will be posted today. All we're going to do on, you know what? How about I actually do what I was going to do on Wednesday today, and we just use Wednesday as another kind of review day thing before the test. Does that sound okay to you guys? All right. So what I was going to do on Wednesday, but what I'm now going to do today, is we're going to look at a circuit that instead of it being an RLC circuit, it's just going to be a generic second order circuit, meaning that it's going to have 2 energy storage elements that can't be combined into a single equivalent thing. the laziest thing to do would be to literally do the exact same circuit I just did, but replace one of the inductors with, or replace the inductor with a capacitor, or replace the capacitor with an inductor. But let's try to make something slightly different. I think I need to add another resistor in here, or it's not going to work the way that I want it to. So let's call this, we'll leave that. All right, so here will be let's just call it I1. And let's call this guy I2. This will be V1. And this will be V2. Hopefully this doesn't wind up being too difficult, right? So this is a generic second order circuit because there are two energy storage elements that cannot be combined into a single equivalent energy storage element during the transient condition, right? So during the transient condition, effectively, if I looked at a dead network, I would have R3 in parallel with a series combination of R1 and L1 in parallel with the series combination of R2 and L2. And there's no way that I can combine that inductance L1 and that inductance L2 into a single equivalent inductance. So this also satisfies the generic case that we're looking at. I'm going to approach the solution in very much the same way, because why break something or why fix something if it isn't broken, right? So I'm going to apply KCL at the top node. So that's going to be, let's say that this current flowing in plus this current flowing in will be equal to these currents flowing out, just for simplicity's sake. So that's going to look like, let's do the easy one first, IS. And now we have to figure out what to do with the current flowing in through resistor R3. So I know for sure that it's going to be something over R3. And it's definitely going to be VS minus something based on the direction of the current. But now I have a couple of options here, right? So I can choose to express the second voltage, or the voltage on the right-hand side of the resistor R3, as the voltage drop across the resistor R1 in series with the voltage drop across the inductor L1, or the voltage drop across the resistor R2 in series with the voltage drop across the inductor L2. Either one should wind up working, so I'm just going to say it's R1, excuse me, R1, I1 plus V1. Oops, and that bracket shouldn't go down to the bottom. That just looks weird. So those are my currents flowing in. And this is going to equal to my currents flowing out. which is I1 plus I2. So let's do a bit of rearranging here. Effectively, I'm going to isolate I2 by itself because that seems like it's going to be pretty easy to do. And so this should be equal to IS plus VS over R3. Then I'm going to have minus R1 over R3 times I1 minus V1 over R3. We know that we can express V1 in terms of I1. So that's going to be L over R3 I1. And then I'll also have a minus I1 term from moving this guy to the other side of the equal sign. So because the algebra is so critical here, have I made any mistakes with my substitutions or moving anything around? Isaiah, yes, sir. So this V1 right here could be written as L times the derivative. Oh, so that's, I made a mistake. Thank you for that. So let me squeeze that derivative in. Thank you very much for that catch, Isaiah. Is that better? Yeah. And so now I have I2 expressed purely in terms of I1. I'm going to take one more step here and just lump some things together. So I have this constant term of IS plus VS over R3. I'm putting the brackets around it clearly, or just to say this is a constant term. So if I wind up taking the derivative of this, that part's going to go to 0. Let's factor out a negative sign here, and let's do my 0th derivative terms. So I'm going to have 1 plus R1 over R3 times I1 minus L over R3 times the derivative of I1. I don't think I can simplify that one any further, so let's call that number 1. All right, so I think now I'm going to do KVL. Effectively around this middle loop. I'm going to choose to write it as the voltage drop, total voltage drop across that left-hand leg will be equal to the total voltage drop across that right-hand leg because they're in parallel with each other. So that's going to look like R1, dang it, I keep doing it, I1 plus V1 is equal to R2 I2 plus V2. And so now I can substitute in for V1 and V2. So that'll be R1 I1 plus L di1 by dt is equal to R2 I2 plus L2 di2 by dt. My different variables are already isolated on opposite sides of an equal sign, so that one seems like pretty legit. And looking at things now, if I take the derivative of equation 1, that'll get me the derivative of I2, and that would allow me to substitute equation 1 and the derivative of equation 1 into equation 2 to get my second order differential equation. So it's the same basic thing, it's just now we have only inductors instead of an inductor and a capacitor. All right, so for equation 3, I can say that the derivative of my current I2 is equal to negative 1 plus R1 over R3 times the derivative of I1 minus L over R3 times the second derivative of I1. Let's call this guy equation 3. And once again, we're going to sub 1 and 3 into 2. So that would be R1 I1 plus L di1 by dt is equal to R2 times effectively equation 1. You're going to need a bigger bracket. One and 3 into 2. And then I need to add to this L2 times equation 3. And now my expression is only in terms of inductor current I1, and it's just moving stuff around to get it into the form we want, which I guess I can actually do. All right, so sorry, this son of a bitch. Hold on, let me think about things here, because I just have a random L here and I don't remember if it's L1 or L2, so we need to sort that out. And I did the same thing here and here. So that should have been, this one's definitely L1, which means this one's definitely L1. L1, L1, L1. I think I got all of them. Looks like all of the ones that were missing were associated with inductor 1. Okay. Sorry about that. Oh goodness. Okay, so I'm gonna move all of my inductor current terms to the left-hand side of the equal sign. So effectively all of these negative signs on the right-hand side of the equal sign are going to wind up going away. I'm going to start with my second derivative term. So that's going to look like L1 times L2 divided by R3 times the second derivative of I1 with respect to time. Little check mark here. That's my only second derivative term, so that one seems okay. Now I'm going to have my first derivative terms. So from this guy right here, I have an L1. It looks like I'm going to have an L1 times R2 over R3 from this guy right here, right? This R2 is being multiplied by that fraction. So I move the L1 to the outside, have R2 over R3, so I think that's okay. Then I'm going to have plus L2 times 1 plus R1 over R3. That is from this term right here. This is multiplied by the derivative of I1 with respect to time. Now I will have my just I1 terms. So I have an R1 from this guy. And then I will have a R2 times 1 plus R1 over R3 from this guy right here. And all of this is equal to R2 times IS plus BS over R3. So by looking at this thing, alpha is going to be, so let's see, we're going to have L1 times 1 plus R2 over R3 plus L2 times 1 plus R1 over R3 divided by twice L1 times L2 over R3. And omega naught is going to be I have an incredulous look on my face for those of you that are wondering, because I'm surprised that the inductor value doesn't have anything to do with omega naught at all. But I might have made an algebraic error somewhere. But the process is the correct for what it's worth. R1 plus R2 times 1 plus R1 over R3. So just for heads up here, your take-home test is going to be literally one of these problems, because they can be a bit of a pain in the butt. Amir, I think you had your hand up. Okay. Yeah.
So it's the last take-home
Yep, that's exactly what you're gonna get is 1 week. Mhm. Michael,
So, first exam, is all of the lessons right before it? Analysis 1 to 5. Or is it just the first two that?
it is series RLC circuits and parallel RLC circuits. That's it. You will have one series RLC and one parallel RLC on your in-class portion of your exam. So if, like I said earlier, if you have done okay with, I think, homework number 8 and homework number 9, the in-class portion of the exam should be pretty simple. Yep. And then the take-home portion will be similar to, I think we're going to be up to homework number 10. So for homework number 10, I'm going to ask you to work 2 of these things. Yeah. And then the in-class portion, yeah, the take-home portion is one of these type of problems. What? I did 2 of them here in less than an hour.
Well, I mean, how long have you been doing this?
I think I added this into the curriculum for circuits 2 about 2 years ago.
No, but how long have you known about how to do this?
From about 2 years ago.
Well,
Yeah, and I'm giving you a week to do it when I gave myself an hour and 15 minutes. So I feel like that's pretty fair. Has the homework been due 2 class periods? Then yes, it'll be due on Friday. Yeah. All right. Yes, Toby. Alpha comes from, let's go way back up here. Alpha is b over 2, where b is the coefficient of the first derivative term. Omega naught is the square root of c, where c is the coefficient of the 0th derivative term, or just the current or voltage by itself.
The coefficient of the second. Yeah. It's on the bottom. Yeah, we're doing.
Oh, that's where it came. Okay, sorry, I made a mistake. Thank you for that. That's my incredulousness should be gone now. There we go. So my expectation, so let me clarify this. So that was a very, very good question. My expectation is that the coefficient for my second derivative term is supposed to be 1. So that's why I'm dividing the coefficient of my first derivative term by the coefficient of my second derivative term. And I'm dividing my constant term by the coefficient of my second derivative term. Everything here at the end just got divided by 2 times L1 over, or L1, L2 divided by R3. So I missed that. So thank you for that. Hero.
Why is it a 2 and not 3 dividing by?
Son of a bitch. Yeah. Algebra is hard. I've been working on a circuits 1 test for like 30 hours.
R3 down there.
It's R3. Okay. Oh, June. How do I put this? If you use Laplace in this class, I will not give you credit for it. When we get to circuits 3, where we are going to be dealing with higher than second order circuits and dealing with transient analysis, then we will use Laplace because it is practically impossible to do it otherwise. But because not everybody has had Math 245, I'm not giving anybody credit for having Math 245. But yes, Laplace is easier. Nope. If you use Laplace transform on this stuff, you will not receive credit. The 2 is correct for the alpha term because it should be B over 2. So if we scroll back up here, just to be really clear here, alpha is just the coefficient of the first derivative term divided by 2 when we have a coefficient of 1 as our second derivative term. Yeah. All right.